Welcome to our seminar this week. We're going to talk about medium voltage drives. Now, we had a seminar some time ago about when you're not quite sure whether you want to use a medium voltage drive or a low voltage drive. And so that seminar you can see online. But this one is assuming that we're just going to buy a medium voltage drive. And when you specify a medium voltage drive, what should you really look for? Now, when you specify a low voltage drive, unless you're getting something special, most low voltage drives are pretty similar. They work in a similar way. They have the same topology and so on. Medium voltage drives, not so much. And so even though you would think the only difference between a medium voltage drive and a low voltage drive is the voltage, that's not at all true. In fact, they are almost like a transformer and a panel board. Just almost like completely different products. That, of course, maybe is a little overstated. Now, if you've been on previous webinars, you'll know that I tried my best to keep things non-promotional and basically give you good information that you can use without promoting certain products and making it just into advertising. But obviously, we have to have some examples. And I have chosen today for an example for medium voltage drives to use T-Mic. That, of course, is a manufacturer. Toshiba was a very large manufacturer of medium voltage drives, as was Mitsubishi. And in the United States, the two manufacturers were GE and Westinghouse. I was there when Westinghouse kind of exited the medium voltage drives and systems drives businesses, leaving GE as the only manufacturer. Well, GE, Toshiba, and Mitsubishi combined into a single company, and that company was called T-Mic GE, which is now just T-Mic, stands for Toshiba Mitsubishi Electrical Industrial Corporation. And because they inherited the product lines of all those three companies, they have lots and lots of different products. And so you will see many of the slides that I'm using are from that company, excellent company. And aside from using their slides, I won't do a lot of other promotional stuff, but they're an excellent company. So we're going to look at this from a top 10 point of view, and you'll notice in the upper right, that's number one. This will be number one of the top 10. I have not organized these from least important to most important, or vice versa. They are just the top 10 things that I believe that should be considered when purchasing a medium voltage drive. And they are my opinions, so you can take it there. The first thing is the application. Now, most medium voltage drives are put on fans, pumps, or conveyors, but there are a lot of more difficult applications. The biggest reason why variable frequency drives or adjustable speed drives are used, regardless whether it's low voltage or medium voltage, is for energy savings. Now, these are the market share in these various applications. And as you can see, with industrial electricity, motors use about 57% of all the electricity used in industrial plants. If we look at industrial motor loads, 15% of those on drives are compressors, 40% on pumps, 30% on fans. And so you can see why that's a pretty important application for variable frequency drives. 97% of motors in the United States are running across the line. That's an ABB study. And if we were to use variable frequency drives in places where they could save energy, we could save approximately 7% of the global electricity demand. So that's a pretty significant thing. Here's some of the applications. You can see that we find medium voltage drives. I won't go over each of those. Let me just mention that there are two types of drives, and here I'm being simplistic, but I'm going to segregate big drives into two categories. One category is your standalone drive, and a second category is your systems drive. So you can see there in that top picture, I was the director of engineering for a steel plant, the only integrated steel plant in the Western United States, Geneva Steel. And that's not a picture of Geneva Steel, but it looks somewhat like it. Now, we had a broadside mill that was 50,000 horsepower, And then it went through 6 finishing stands that hit about 12,000 horsepower. The peak torques were extremely high as compared to the average torques. And you could have a strand of steel or a billet of steel in all 6 mills at the same time. And each mill goes a little bit faster than the others because you're rolling that steel out. Well, in a situation like this, it's extremely important to have all those drives integrated together with high-speed communications, because everything has to operate exactly right, or you end up with a huge crash and lose lots of money and can damage things. So this would be an example, certainly not the only example, but an example of a systems drive. And systems drives are meant to operate as complete systems. They're much more complicated than standalone drives. So when you look at drives manufacturers, it used to be there were only a few medium voltage drives manufacturers. Now it seems like everybody's getting into the business. But most of the medium voltage drives manufacturers go towards the fans, pumps, and compressors and just really produce standalone drives. And it's a smaller subset of people who produce the systems drives that are able to produce full systems, like in steel mills, paper mills, material handling, and things of that sort. Here's some more applications. Testing is a big market for medium voltage drives, and of course, electric utilities and power plants. So the application is very important. If you have a very simple application, you can use a simple drive. If you need a more complicated application, you're going to need a more complicated drive and maybe a systems drive. And it's important that whatever manufacturer you use, that they have significant experience, not only in that area, but in that particular application that you're looking for. Now, next, let's look at motor and system voltage. If you have a low voltage drive, typically, if you've got a 208 volt system, you get a 208 volt drive, you feed it with 208 volts, it puts out 208 volts, and you use a 208 volt motor. That's not 100% true, but it's like 99.9% true. With medium voltage drives, that is not true. It is very, very common to have the voltage going into the drive be different than the voltage coming out of the drive. And so when we go to a medium voltage drive, we don't just say, hey, I need a 4160 volt drive. The question is, what voltage is your motor and what voltage is your power system? And we can have a different voltage coming into the drive than going out of the drive. Now, one of the ways that, or one of the reasons for that is that most medium voltage drives will include an isolation transformer. This is point number 3. I believe that all medium voltage drives should have an isolation transformer. Now, some people would disagree with me about that, and it has become more popular in recent years to use what they call a direct-to-drive solution, in which you do not have an isolation transformer. But there are many advantages of an isolation transformer, and my personal opinion is, don't cut corners. Get a drive that has a full isolation transformer. Now, I have some slides here that I am not going to cover in detail that talk about how isolation transformers protect the motor from high voltages. And I am not going to go through these because of time. And also, I think a lot of the people tuned into this probably, I would see their eyes rolling in their back of the head when we get into specific details. But this presentation is available to you for download. So if you want to go through these details, and it'll take you probably 15 minutes to carefully look at this and analyze it and understand how isolation transformers protect the motors, then I think it will be worth your time if you have that kind of interest. So here's the slides in which we go through talking about how isolation transformers protect drives from motors, the other way around, motors from drives and high voltages. There are typically 2 drives technologies out there, voltage source and current source. I only know of one manufacturer that's still making a current source. Everybody else, everyone used to have current source that made medium voltage drives, but they've largely been replaced by voltage source drives. And so we could talk about those 2, but I'm not going to spend a lot of time on current source versus voltage source because pretty much the market has moved towards voltage source drives. Here's some more information giving us an example of voltages on these drives. So I'll let you do that on your own. Let's look at additional benefits of isolation transformers. Number one, it can be used to shift phases, currents, and voltages and thus reduce harmonics. So if you have a multi-pulse drive, that would be a 12-pulse drive, an 18-pulse drive, a 24-pulse drive, and so on, you really have to have an isolation transformer. Second, it protects the drive and the motor from surges and dangerous power line disturbances. We've talked about that a bit, although you'll have to go through those slides to appreciate it a little bit more. Obviously, when you get disturbances in voltage and transient voltages and so on, having that isolation transformer is very good for protecting your system. Now, it allows the drive to be directly connected to higher voltage distribution system while providing a low voltage output to the motor, and we have talked about that. Next, when multiple drives or other medium voltage drives are all directly connected to the same plant bus, a fault or a ground on one piece of equipment can induce faults on its neighbors. In the steel industry, we used to be all DC. And in fact, my plant, the Geneva plant, we had MG sets. So we would come in to a synchronous motor with AC. That synchronous motor would be connected on its shaft to a DC generator. And then that DC generator would be connected to a DC motor. That was 1940s technology. And always on our DC drives. And we had a lot of DC drives, you know, as time went on. In 1961, GE came out with the silicon controlled rectifier, and we started being able to produce solid state drives. So we didn't have to have those MG sets, and we could go directly from the line to a DC motor. We always used isolation transformers on our DC drives to protect them from the ground faults, and also for some other reasons that I won't get into. So isolating drives from one another is a very good idea. Now, this is something that you don't see in low voltage drives. It's called neutral point clamping. And basically, the reason you don't see it in low voltage drives is because you can't afford it. In low voltage drives, you have to minimize the number of diodes, the number of IGBTs in there in order to have a drive that will be cost effective. And so you just don't have the money to do this. But in medium voltage drives, you can actually connect the power switches to a zero level, effectively creating a neutral clamping point for the motor, and that keeps your motor voltages where you want them. Let me mention a little bit about motors. If you have a low voltage motor, you really need to make sure that that low voltage motor has what we call high spike wire, or it's VFD compatible. And we generally refer to NEMA MG1 part 31. NEMA MG1 part 30 is for regular motors, specifies 1000 volt insulation, and NEMA MG1 part 31 is for motors used on VFDs. And it specifies motors, I'm going to say 1600 volt insulation, because that's the actual insulation that a lot of these are built to, although the standard is a little bit lower, that closer to 1500 volts. But the point is they have premium insulation on them. Well, when you get into medium voltage motors, there is no such thing. You don't have regular motors and VFD rated motors. They're just medium voltage motors. And so it becomes more important than ever to make sure and to control those voltage spikes. Fortunately, manufacturers of medium voltage drives have responded to that, and the output waveforms are much better on a medium voltage drive than they are on a low voltage drive, which I will show you coming up. Now let's talk about power quality a little bit, because power quality is one of our biggest problems on low voltage drives, particularly harmonics. And we had a full seminar on harmonics, concentrating on VFD harmonics. Previously, we were looking at low voltage drives. Today, we're going to look at these things with regard to medium voltage drives. So this is the beer analogy, and this is power factor. In this case, I'm specifically talking about displacement power factor, although this could apply really to any. It shows a mug of beer here, and we have about 65% of that mug is actual beer. Then we have the foam, and the apparent beer is the size of the mug. So really, when you buy that mug, you only get about 65% of it in terms of the beer that you can drink. Displacement power factor, and really all power factors are similar to this. in that the useful work we get out of current is we call watts, and the wasted capacity, that would be the foam, would be VARs, and then those two together are the kVA. So if we look at it in terms of amps rather than volt amps, if you have 100 amps, you might find that only 65 of those amps are actually doing real work, and the rest of them are just being used for magnetization and harmonics and things of that sort. So in this case, we take the watts divided by the kVA, and again, that would be 65%. It's pretty much the same analogy. This tells you how much of your current you're actually using to generate real power. And in general, the higher the power factor, the better. In facilities, the utility has to supply the active power and the reactive power. That reactive power has to be generated in their generators, transmitted across their transmission lines, put through the transformers, put through the distribution system, and yet it doesn't actually generate real power. And so the higher the power factor, the lower that kVAR is going to be, and we'll be able to produce the same amount of load with a lower amount of current. And we won't get into that in a lot more detail because we had a power factor seminar in which we did get into it in a great deal more detail. So you can check that out if you're interested. Now, it's also interesting, a lot of people don't think about this, but on systems, and particularly on medium voltage systems, your voltage drops are primarily proportional to your VARs, not to your kilowatts. That's obviously not 100% true, but a higher power factor will give you better voltage regulation. So if your voltage is up and down quite a bit and you increase the power factor, then you will decrease your voltage regulation. Your voltage now will be tighter, and that will help everything in your plant, help your motors, help your loads, help everything. Voltage source drives tend to have very low reactive power. And so whether it's low voltage or medium voltage drives in general have very good displacement power factor. Now, some medium voltage drives, I don't know any low voltage drive that can do this, but some medium voltage drives with an active front end can actually supply VARs. So if you have a low power factor and you put in a certain type of medium voltage drive, not only can it run the motor for you, but it can also regulate your power factor, and it can provide VARs back into the system in order to compensate for other loads and bring your power factor on your system up. So, and that kind of comes free. Anything that you don't need to go to the motor, you can use to correct for power factor. So an interesting possibility. Now, harmonics, again, we had a whole harmonics seminar, but harmonics are like any other kind of pollution. Harmonics pollute electrical lines. Other types of pollution produce other types of problems. Now, this is a standard 6-pulse converter. We could think of this more as a low voltage drive, although some medium voltage drives can look like this as well, but not too many of the quality ones. And you can see that current is anything but a sine wave. And so because the current is distorted like that, it's going to generate high frequency noise. And when you think of harmonics or bad power, generally we're talking about high frequency noise that is being created by the drive and being put back on the power distribution system. These are some of the effects of harmonics. I'm not going to go through these. Just suffice it to say that harmonics can cause a lot of problems in your power distribution system. And we would like to keep current harmonics within the IEEE level and voltage harmonics within the IEEE level. Here is the IEEE. It's produced by the utility, IEEE 519. Latest version is 2014. And if you look over there on the right, you see a column called TDD. That stands for total demand distortion. And basically, it is your total current distortion at your highest load during the month, or basically your load when you set your utility demand. So your current distortion could go anywhere from 5 to 20%. Typically on systems, 12 to 15% is sufficient. However, the larger the drive, the more likely it is that we're going to need better. And on medium voltage drives, it's very easy to get quality medium voltage drives that are under 5%, and you don't have to pay a premium for that. So on low voltage drives, we don't necessarily go to 5% because it's very, very difficult to get there. On medium voltage drives, it's not. It is just not difficult to get there. And so buy a good quality medium voltage drive. You should ask for a drive with not more than 5% total current distortion. Now here is 3 technologies of drives. All of these are T-mic drives, and we will look at the technologies here in just a minute. But the Durabuilt is kind of an older drive, but still being sold, very, very fine drive. Its power factor, we're talking about displacement power factor, is over 95%, and total harmonic current distortion maybe around 3%. The MVG is a different technology. We'll talk about it in a minute and when we get into topologies. And again, you can see the power factor and the current distortion. The MVE2 is the most recent technology. It's got an active front end, and you can see it's got a power factor of 100%. Now, typically, I used to say, oh, you get over 95% power factor, you're good, don't worry about it. And there's still something to be said for that. But think about it, if you have 100% power factor, you're actually powering your load on 5% less current than if you have a 95% power factor. So when you get into very large drives, there is something to be said for 100% power factor. And that drive will actually control the power factor so that it's 100% at basically all speeds and loads. And your total harmonic distortion is approximately 2%. Now, this is probably the most interesting part of the presentation for me, I guess because I'm a geek. But this is the timeline in which we developed medium voltage drives. You'll notice on the top we have transistors, and on the bottom we have thyristors. Now, GE came out with the silicon controlled rectifier, as I say, in 1961. The diode was already there by that time. And so let me pull in that SCR. That was the first thing that allowed us to develop DC drives. Now, an SCR can turn current on. It's like a gate valve. If you pull the latch, the gate opens, and you can therefore control your current by turning it on. The problem is you can't turn it off. And so you have to have a drive topology that allows you to force the current to go in the reverse direction in order to get that turned off. Now, shortly after GE introduced the silicon controlled rectifier, Westinghouse, who was the other big electric company at the time, introduced their silicon controlled rectifier, but they called it a thyristor. And so for a while there, if you bought it from GE, it was an SCR. If you bought it from Westinghouse, it was a thyristor. These days, we have generally said that that particular device that GE invented, we still call a silicon controlled rectifier, whereas thyristor now means any bistable device that you can turn on but can't turn off. And so that's why that lower section we're calling a thyristor, because it's a more general term for other types of devices that still can have the same functionality. Now, the load commutated inverters there on the bottom, that used SCRs, but we required synchronous motors with that. About 1975, bipolar transistors came out, and they were really cool because a bipolar transistor you can turn on and you can turn it off. But we didn't really use it in large devices because it was not available in high voltages and in high current ratings. Well, then we came out with the gate turn-off thyristor. Now we're back on the bottom part of the line, and frankly, we don't want to be on the bottom of that line. We want to be on the top of that line, because if you have to find ways of reversing the current or injecting huge amounts of current into the gate to turn it off, that just makes for a drive that is more complicated and less reliable. But the gate turn-off thyristor could do what we couldn't get a transistor to do. And so in the early 80s, a lot of drives, both low voltage and medium voltage drives, started to use gate turn-off thyristors. Then we came out with the IGBT. Now, the IGBT came out in about 1987, was in drives about 1988, developed by the Japanese. It's called an insulated gate bipolar transistor, and for the first time, we could turn these things on and off with very, very low amounts of voltage and current. So on that gate, we could turn this on very easily, and that got rid of a lot of circuitry in drives, made them far more reliable, and the IGBT revolutionized low voltage drives, but not available in medium voltage. So then along came the integrated gate commutated thyristor, and I'm going to move along a little bit because of time. And finally, we got a medium voltage insulated gate bipolar transistor, and that changed the medium voltage drive market because for the first time, we could now turn on and off medium voltage with devices that required very low amounts of power in their gate. Then came out a symmetrical gate commutating thyristor. And again, that's on the thyristor line, not where I want to live, but nevertheless could accommodate voltages and currents that we couldn't get from IGBTs at the time. Then came an injection enhanced gate transistor. That's again a transistor. There's only one manufacturer that makes it. You might guess that's T-Mike. And it's a monster. I will show you in a minute. This is an IGBT. If I looked at that, nobody told me, I wouldn't know whether that was a low voltage or a medium voltage IGBT. They tend to look alike, but a tremendous development in drives that really revolutionized drive technology. This particular one is 400 amps and 3,300 volts. Now an IGT is the latest generation. It can go up to 4,500 volts and 4,000 amps. I like pictures better, you might be able to tell. That's an IGT, and you can compare it to a calculator there. Look how small that is, and that can 4,500 volts and 4,000 amps. It's amazing that any device can do that. And if you buy a 1,000, 2,000, 3,000 horsepower drive, you're not going to get IGTs because you can't afford them. But when you get into very large, north of 10,000 horsepower, then you may be in the range where you can afford to use IEGTs. And that's kind of, to me, the latest and most amazing device available. Now let's look at our output levels. I think this is very, very important. What you're looking at is a low voltage drive. And basically, if we turn on that top IGBT, it gives us positive voltage. If we turn on the bottom one, it gets negative voltage. That's an oversimplification, but it's good enough for our use today. And so you look at this waveform up here, and you've got your 0 voltage, then your high voltage, which on a 480 volt drive might be 650 volts. And basically you got this picket fence where you're just turning that voltage on and off and on and off, and you can turn it off and on and off in the positive direction and the negative direction. And by using PWM technology, varying the width of those pulses, you get a current waveform. That's not a great voltage waveform, and we have a lot of problems. That voltage waveform is the reason why we have to have higher insulation on low voltage motors, because it creates really high voltages. You're going from 0 to 650 volts almost instantly, I mean very quickly, and that causes some real problems with our insulation. But all low voltage drives are built that way. That's just the way the world is. Now, I'm going to call this a 2/3 level drive. Power system engineers would call that a 2-level drive. It's a 2-level drive because it has 2 levels between 0 and peak. So from 0 to peak, it's 2 levels. From peak to peak, there's 1 level, 2 levels, and 3 levels. It has 3-level drives. So I'm going to call this 2-level drive a 2/3, and that is the way all low voltage drives are created. Now I've got my 2-level drive up here, but now down here I'm showing you a 3-level drive. A 3-level drive takes more semiconductors, and therefore that's why we can't afford it in low voltage. So this is a 3-level drive that gives you 3 levels from 0 to peak and 5 levels from peak to peak. You'll notice there's our 0 voltage, and so that's 1 voltage, 2nd voltage, 3rd voltage. There's 3 levels, and that is a huge advance in technology, because now you're only turning on half of that voltage at a time. So the motor is only seeing half voltage at a time. It's much easier on motor insulation, which we really need in a medium voltage drive. Now, my opinion, here again, other people might disagree with me, but I would stand by this, that 3-level drive is okay for 2,300 volts. Anything above 2,300 volts, I think a 3-level drive is just not cutting it these days. And 3-level drives still can cause voltage problems, especially at 4160, 6600. And you have to worry about the length of the cable between the drive and the motor and so on. So on a 2300 volt drive, I'm okay with the 3-level. Higher voltage, I really would like something better. Is there something better? Well, yes, there's a 5-level drive. And so you can see here on the lower right, that's a 5-level. For the first time, that starts to look to me like a sine wave. And that's what we'd really like to see out of a drive. You'll notice that this 5-level drive has 5 levels from 0 to peak. There's 1, 2, 3, 4, and 5. So you're only turning on 1/4 or 25% of the voltage at the time. And now I think this used to be state of the art. I still think it's very, very good in terms of producing a good output waveform to the motor that's not going to cause insulation issues. Can you do better? Well, yes, you can. Here is a drive. This is a topology where you can see we use lower voltage cells and put them in series. And this particular drive is actually a 25-level drive. Pretty amazing. And so in reality, of course, the more levels, the better, although there comes a point at which you're not really getting a lot for your money as you increase those levels. The higher the voltage, the more levels I would like to see. So this is the latest and greatest in technology. This is a T-Mic MVE2. It's an active front-end drive. You'll notice that it is 9 levels for the 4160 volt version, 13 levels for the 6600 volt version, and 21 levels when you get to 10 or 11 kV. So 9 levels from 0 to peak, 17 levels from peak to peak. And if you look at that, man, that's a sine wave. It also has 100% power factor, as we talked about, and 2% total harmonic distortion. It also is regenerative. Most drives, whether they be low voltage or medium voltage drives, are not regenerative. If you try to slow a drive down too fast, or you've got something where water pressure is pushing the drive, or you've got a downhill conveyor or something, that drive is simply going to trip. This particular drive, because it has an active front end, is also regenerative. And this particular drive can also supply VARs to you if you want to use the excess capacity in that drive to correct your power factor in your building. That's a picture of the MVE2 drive. It's got an isolation transformer, and then your converter and your inverter are in the cells. This is the Durabuilt 5i. Now that is a multi-pulse type of drive. This particular drive is a 24 pulse. In my opinion, I would like to see 24 pulse on minimum on everything. 12 pulse is certainly much better than 6 pulse, and 18 pulse is getting pretty good, but I think in a medium voltage drive domain, you really deserve at least a 24 pulse drive. 24 pulse drive is going to get you well below 5% in terms of your harmonics and give you a very, very good waveform that you can see there. So this particular drive has a 24 pulse input and a 5-level output, which is pretty good. And there is a picture of that. Again, there's the isolation transformer, and then you have your converters and your inverters downstream. Now, this was a technology, I tend to call it the Robicon technology. Robicon popularized this in the United States and patented it, although T-Mic was actually making these before Robicon was. But a lot of people think of this as the Robicon technology. Basically, you use a transformer with lots of secondary windings, and you use low voltage converters and inverters and put them in the inverter in series in order to generate your output waveform. Again, T-Mic has this technology as well. And you can see down here at the various voltages, the number of pulses and the number of levels. So the lowest level we get is a 7 level. That's the output to the motor. And the pulses has to do with the utility. And it's 18 pulse, but only in the 2400 volt version. And then you get to 24 and even as high as 54 pulses. We will talk about this in a moment, but when we talked about low voltage versus medium voltage, reliability was a huge concern. Medium voltage drives are much, much, much more reliable than low voltage drives. Some medium voltage drives are much better than others. If you look at a drive in the steel industry, for instance, when we had an outage, we'd lose $100,000 an hour. So we just can't afford that. And we certainly can't afford to call the company that manufactures the drive and have them say, yeah, we can get to you in 2 weeks. No, we want 3 people on the plane in 3 hours. And so in applications like that, you get a company that can produce those types of drives, you're going to get a very, very reliable drive, and you're going to have a very good service capability. There's the MBG2 drive, and so that's the third technology. Now, all of these technologies are slightly different, but basically we have the 3 technologies available. The active front end, like with the MBE2, we've got the Durabelt, which has a 24 pulse input, and then your medium voltage transistors on the output that give you a 5 pulse or a 5 level output. And then this Robocon technology where we're using lower voltage cells and putting them in series. And again, that's a little bit of an oversimplification, but I think it's fair. There's a lot of other drives that T-Mike has. I just picked this one because I think it's impressive. That's a 30 MVA, or about a 30,000 horsepower lineup. And if you put 4 of them in parallel, you can get 120,000 MVA, which would be more than 120,000 horsepower. Do drives get that big? Yeah, you get into some really, really big medium voltage drives. And in this case, this is a 5 level output. You can see the output waveform there. Now, conservative design, we want to look at a drive that's very, very conservatively designed. When you manufacture a drive, how do you do the transformer? How do you do the converters? How big a diodes do you get? How big a IGBTs do you get? How conservative you are? Well, it's very difficult to know what that is. My opinion is if you want reliability, you should do 3 things. Number 1, look for field-proven reliability. You can get some statistics on that. Second, look for drives that are used in applications that require just the utmost reliability. And the most difficult application in the world that requires the highest reliability are steel mills. So if you look at drives that are very popular in steel plants, that's a lot of, you've got to have a reliable drive. And third, you can go by reputation, talking to people who have these drives and ask them how reliable they are. Number 8, we're getting into reliability itself. In the past, people were scared of medium voltage drives because there were a lot of horror stories having to do with medium voltage drives. And common concerns was they're unreliable, the really big ones unreliable, they're scary, they're dangerous, they're difficult and costly to repair. And all of those issues have been solved, really. And they are much more reliable than a low voltage drive. They have excellent harmonics, excellent power factor, excellent waveforms to the motor that protect the motor from high voltages. And they are actually safer than a low voltage drive to work on because you are never allowed to get near the medium voltage components. In order to get to the medium voltage components, you actually have to use Kirk key interlocks to shut off all your power, so that really these things are much safer to work on than low voltage. Low voltage, you open up the door and there's 480 volts right there. That's not the case here. So these are some of the reliability statistics from T-Mike. You can see that the events, and they track all of these things, and this particular drive has about a 15.8 year mean time between failure. Here's a water-cooled VFD that actually has a 28.4 year mean time between failures. Those are just extremely good numbers. And here's some of the factors that you get into with reliability. You can just glance through there. I'm not going to go through that in detail due to time. Reliability can be improved by reducing the parts count, by being very conservative in your application of the IGBTs and the power devices. T-Mike's opinion is these things are so reliable that some manufacturers will say, oh, we're going to give you extra cells and we'll have N+1 reliability. So if a cell fails, then we can continue operating. If you've got 15, 20 year reliability, generally more components is just generally going to reduce your reliability. And my personal experience with that is that the N+1 generally lowers the reliability rather than increases it. Here's some of the tests that you can do for increased reliability. We generally can afford to do much more extensive testing on a medium voltage drive than these low voltage drives that are running off the assembly line, although many low voltage drives get tested pretty well as well. Here's some more reliability improvement by testing of the components and testing of the input waveforms and the output waveforms. And then we do a complete drive and system test using a real motor. Water cooling, we could spend an hour on water cooling, but with low voltage drives, in most cases, not all, but in most cases, we don't see water cooling. In medium voltage drives, when you get up into the large drives, water cooling just becomes a de facto standard. So water cooling dissipates higher levels of heat, has a smaller drive footprint, has lower noise levels, is more resistant to contamination of the air and in the facility. So water-cooled drives keep that drive very clean. And because water-cooled reduces heat into the room, you need less air conditioning in the room. And you can provide redundancy in pumps and fans and so on. Turns out water-cooled drives are actually even more reliable than air-cooled drives. And I showed you that one water-cooled drive that was a 28-year mean time between failure. Here's an example at 10,000 horsepower of an air-cooled drive versus a water-cooled drive. So you can see the reduction in size. And as you get up into multiple tens of thousands of horsepower, you just really have to go to a water-cooled drive. There's your fleet reliability. Again, they go from 15 to 20 to 40 years mean time between failure. I can tell you that we just haven't, of all the drives we've sold, we've never had a major failure on a medium voltage drive. So it's a pretty good, I love medium voltage drives if you can't tell. Engineering support, this is for engineering, not field service. T-Mike has more engineers in the United States. A lot of the other manufacturers or engineers are in Europe. And this is the Roanoke factory in Virginia. That was the GE plant. And when GE combined with Toshiba and Mitsubishi, then they kept that. There's about 100 full-time degreed electrical engineers that only do medium voltage drives there. And no matter what your application, there's probably somebody who's done it and who is an expert on that. These are training rooms. And if you have a systems drive, you can actually go back and simulate your whole system on simulators back there. This is my last point, and that is field service. In low voltage drives as well as medium voltage drives, I've heard the statement made that the only thing to worry about when buying a drive is the service. Who's selling it to you and how well can they service you? Well, I think that's an overstatement. I think that there's a big difference in the reliability of drives and the performance of drives, but I certainly agree that service is really critical. And especially in medium voltage, there's a lot fewer people that can service medium voltage than can service low voltage. So T-Mike has 70 service engineers in the United States that are dedicated to medium voltage, all of them degreed engineers. Energy Management, the company I work for, we have 3 people that are certified and specialize in medium voltage drives. So we like to think we have excellent support in North America, both our own company and T-Mike generally throughout the United States. Drives typically have a 30 good drives, 30-minute mean time repair, and some people could say 15 or 20 minutes, but you know, it takes time just to go up there and open the doors and so on. 30 minutes is pretty quickly, and these cells basically just, they just slide out and slide in. Drive control software, we generally control and troubleshoot a medium voltage drive remotely. And so you can go back to that Virginia facility, or you can come to our facility in Salt Lake, and we can actually get in. And if you allow us to, of course, that's a firewall issue, we can actually go in there and program and run the drive and look at the faults and actually do this remotely, because sometimes when a drive's down, it's really critical. Now, this is a remote connectivity module, something that comes with the T-Mike drives. It is a separate standalone controller that doesn't do anything to control the drive. it's kind of a little watchdog kind of guy, or it's a supervisor that sits outside the drive and just watches what the drive is doing. Because it cannot control the drive in any way, we don't have problems with cyber crime on this because it is isolated from that drive control system, but it's an excellent way for you to see what's going on with the drive in a very safe, cyber safe manner. And if the drive were to blow up and the control board in the drive were to fail, this actually still has all the data so that you can go in and download that and look at it. So there we are, my opinion on the 10 things that you want to look at in a drive. We want to look at the topology, the harmonics, the output waveform in terms of number of levels, and we want to pay very special attention to the reliability, the mean time between failure, the ability to get service engineers, because many companies, it could be 2 weeks before they can get a service guy out. And medium voltage drives, generally, you don't want to wait that long. So that is the end. I will turn the time back to Tyler, and we appreciate you joining our seminar. We are open for questions.
Great. Feel free to keep sending in questions. We do have a couple, though. What site considerations do you need to prepare before medium voltage VFD installation?
Boy, now there's an excellent question. And unfortunately, it gets to be a little more complicated than we can probably answer quickly. But one of the biggest things we look at in a site application is we want to keep that drive clean. We want to keep all drives clean, and we want to get it cooled. So where are you going to put it? Ideally, I would like to put it in a building with air conditioning. And I'm talking here about smaller medium voltage drives, maybe less than 10,000 horsepower. If it's over 10,000, I'm going to definitely go to a water-cooled design. So if I can find a place there, then I'm going to do that. Many people don't have room for that. And so we can actually produce a drive in a NEMA 3R enclosure that does not have air conditioners, but it's built for outdoor use and it uses heat exchangers. Or we can use an e-house in which we have a control house with air conditioners and put the drive in there, but we definitely want it clean. You want to look at what is the motor voltage. In general, if you get a drive with at least 5 levels and preferably more, we don't have to worry about the insulation on that drive, and we generally don't even have to worry about the service factor on that drive. We can really run pretty, I didn't mean drive, motor. We can pretty much run any motor off of a good drive like that. If you get a good drive with harmonics that are less than 5%, you're not really going to have harmonics problems. So I would stay at least with 24 pulsed or an active front end and under 5% harmonics, and you're just not going to have a problem with that. So those are kind of the major site conditions, and site conditions end up being one of our biggest problems. You know, where do we put it? How do we get the conduits to the drive? How are we going to cool the drive? But in a just kind of a short nutshell, I guess that's what that's kind of my 2 bits worth. And if you have specific site considerations that are a concern, you know, we'd be perfectly happy to talk to you about that.
Great. Next question. Is using external transformers with medium VFDs common? Is there anything you need to watch out for there?
Oh, yeah, that's another great question. I'm glad you asked that. The most VFDs are going to come with that transformer integrated into the VFD cabinet. And I like that because it's clean and everything's in one enclosure and so on. And so it's nice. One of the things you get into with medium voltage VFDs that you do not get into with low voltage VFDs is you got a transformer there, and typically lots of cables coming out of the transformer, because you'll have 3 wires going into the transformer, but you may have 9 or 12 or 15 cables or even more coming out of the transformer, coming to these various cells. So obviously, if you take the transformer and locate it remotely, then you're going to have not just 3 cables coming from the transformer, but maybe 15 cables coming from that transformer. But that's not a terrible thing. You know, it's not horrible. Locating the transformer outside gets you some of that heat in the drive outside rather than inside. And if you don't have space inside, then putting the transformer outside certainly can solve some space problems. So is it common? Locating the transformer in the drive is certainly the most common, but it is not uncommon to use transformers that are outside and drives that are inside. That is certainly an option that you can use with medium voltage drive, and certainly an option to be explored. It's like I say, it's nice to have everything in one place inside of a building, but many times there's very good reasons to put that transformer outside, and you certainly can do that with medium voltage drives. Not all medium voltage drives, it'll depend on the drive model and the size and so on, but it's certainly something to be considered.
What warranties are common on medium voltage VFDs, and how do they compare to low voltage VFD warranties?
Typically the warranties on medium, you know that in low voltage and medium voltage drives, the warranty depends on what you want to pay, and you can get a 1-year warranty or a 2-year warranty or a 3 or 5-year warranty. And so if you want a 5-year warranty on drives, for instance, manufacturers will generally increase the price a little bit to cover warranty costs. But medium voltage drives, because they're so highly reliable, those warranty costs tend to be fairly small. Now, when you have a warranty, obviously it's more money because you've got bigger devices and bigger cells and more expensive units. But I would say that warranty is very specific to the manufacturer, and so you're going to see 1 to 5-year warranties generally on both low voltage drives and medium voltage drive. And I'd probably look for maybe a 3-year warranty, but that's something to look at the particular manufacturer for. You don't see warranties that are like 15, 20 years, even though we do see 15 to 20 year mean time between failure, but you don't see drastically longer warranties on medium voltage drives than you do on low voltage.
How often is it recommended to service medium voltage VFDs?
We would recommend on a medium voltage drive to service the VFD at least once a year. Now, when you put in a medium voltage drive, obviously it depends upon where it goes and so on. If you're looking at an air-cooled VFD, typically you're going to have some filters in there or possibly air conditioners. Obviously, I'm going to pay a lot of attention to the air conditioner filters and to the drive filters, and I'm going to see, hey, how clean is it and how dirty are those filters getting? Because you want to keep that drive cool. You want to keep air conditioners cool by not having dirty filters. And so that's kind of the number one thing, is trying to keep those filters clean. I would say once a year, it's a very good idea just to take the drive down and just go through it and take a look at it. It's not like a generator where you're changing the oil or the filters. Generally, there's no parts to change. It's just something where you want to look at it. You want to make sure it's clean. You want to look at any faults that have been there on the controller. And generally, after about 5 years, if you have a very, an application that you need to be extremely reliable, there may need to be some capacitors on the power supply boards or so on that you may want to look at. But typically, there's not a lot of maintenance that goes into these things other than the air filters, but we would recommend that they be looked at once a year, although a lot of them are not.
Okay, is there a specific software program available for design, settings, and troubleshooting? Thanks.
That's an interesting question. And I guess if I understand the question, I'm probably going to say that I don't know of any software program available that lets you go in and design the drive just via a program that asks you questions. In low voltage drives, a lot of times they're standardized, they're on the shelf. You go in there and you say, hey, I want this drive, and it's got this overcurrent setting or overcurrent rating for a minute and so on. And then you look at the model numbers. And medium voltage drives, a lot of times when we go back and we say, what do you got? the answer from TMIC will be, well, what do you want? TMIC drives, as well as all medium voltage drives, from at least from the systems manufacturers, they can have all kinds of ratings depending upon what the load looks like and what the ambient temperature looks like and so on. And so I think it's just more complicated that it would be very difficult to write a simple program that lets you just go through there and answer questions. Now, we do have some simple checklists that you can put in some simple things, but for the most part, if you're going to buy a medium voltage drive, you really probably need to talk to somebody who is experienced and knowledgeable in medium voltage drives so that they can really put their brain on it and look at all the different aspects of that application so that they can recommend the right drive for you. There are some manufacturers that only have one drive. There are other manufacturers, I think TMIC has 13 different models of drives that are used for different applications. So I don't know of anything that just makes this ultra simple.
Great. I think that answers it for the design. They clarified on the settings and troubleshooting, asking if there was any sort of software to communicate with the drives specifically.
Oh, yeah. So I think pretty much I'm more familiar with the TMIC than others, but you definitely is software. And we talked about that remote connectivity module. We put that in there specifically for that purpose. It sits there, it's isolated from the drive. It's basically a little industrial personal computer, and it watches everything that goes on in the drive. With medium voltage drives, you can basically get just about any kind of communication that you'd like. Whether it's Ethernet or Modbus. I've never had somebody say, we want to communicate in this way, and have the drive manufacturer say that they couldn't do it. So very customized, and we do have software packages, of course, that allow you to communicate with the drive, and software packages that allow you to program the drive.
A follow-up question on that one as well. Do these typically come with an HMI?
Yeah, so pretty much all drives will come with some kind of a monitor that's mounted on the front of the drive that will allow you to program it and to see what's going on. That's pretty standard. I don't know of any drive that doesn't have that. And so, yeah, that's even with low voltage drives, we generally have some kind of a keypad on there but that's standard with all medium voltage drives that I'm aware of.
Can you also elaborate on using parallel motors with a single VFD?
Yeah, we don't have a problem with that. Now, let me mention that if you buy, and again, I'm using TMIC just because I'm more familiar with them, and it's not like other manufacturers cannot do this, but we like to use a drive that is tuned to the motor. And so in that case, we would actually tune the drive to the motor when we put it in, and that gives you probably your best performance. And typically, if you're looking for really, really high performance, like say like in Disney World, what's that, the Tower of Terror, that had a TMIC drive on it, that's going to have really high performance. We like to see one drive and one motor, but we commonly do multiple motors on a single drive. And if you do that, you've got to start them the same time. You can't have one motor running on a drive and then just close a contactor and bring the second motor on. You have to really stop the drive and then bring the second motor on and bring both motors up at the same time. But we do that in volts per hertz, and if you've got a fan or pump or compressor, that really works fine. We've got an application that comes to mind in Greeley, Colorado, and we have 5 motors there, and we're putting 2 motors per drive. And our main reason in that case for doing 2 motors per drive was building space, because we didn't have enough room for 4 drives. But there was also a cost issue. It was a lot less expensive to put 2 drives or 2 motors per drive than to have a drive for each of the motors. And it's working really, really well. And there's just on a simple application that doesn't require high performance like a steel mill or a paper mill or something like that, yeah, there's no problem at all using multiple motors on a medium voltage drive.
Are there modeling tools available for the ETAP or SKM? Thanks.
Modeling tools. I know, the ETAP and the SKM are power systems modeling software. In terms of what tools that you have on there, I'm going to probably say no, although I might be lying. I'm not sure really what modeling tools you need. With all drives, even regenerative drives, they do not put power back on a power system in time of a fault. For instance, if you have a fault on a motor, then that motor can feed back into the fault. But if you have a fault on a drive, even if it's regenerative, it doesn't do that. And so basically there's not much in terms of coordination there for regen, or for, it's not even regen, but feeding current back into a fault. So generally when we do an SKM or an ETAP, we just use that as a solid state drive and put in the sizes. And but I don't know that there are special tools that have to do with medium voltage motors, and I could be wrong about that.
All right, that looks like all the questions we had. So we want to thank everyone for joining us. We look forward to seeing you on the next webinar.